Hello, everyone. Welcome to section 2.7. This one is on combining functions. So there's two main ways that we're going to combine functions in this course. The first one is combining functions like algebraically, so with addition, subtraction, multiplication, division. And the other way is going to be through composition. So let's go ahead and take these one at a time. Let's look at algebraic combinations first. So combining functions algebraically. All right, so let's get our setup all straightened out here first. So let f and g be functions. With domains a and b. So here a and b are sets. They're intervals, usually, respectively. So f has domain a and g has domain b. We define the following function combinations. So f plus g of x is going to be just f of x plus g of x. All right, we'll see examples of these here in just a minute. And this will have domain A intersect B. All right. And if we do f minus g of x, that's going to be pretty similar. It's going to be f of x minus g of x. And that will also have domain A intersect B. Okay, now let's look at f times g of x. You're probably going to already guess what's going to come. It's going to be f of x times g of x. And that will also have domain A intersect B. And last, but of course not least, we have f divided by g of x. And again, yes, that is equal to f of x divided by g of x. And the domain for this one is a little bit different. It's going to be A intersect B, and is intersecting with, everywhere g of x is not equal to 0. So the domain for this is going to be A intersect B intersect the set where g of x is not 0. And we'll see an example of this in a minute. It's like what exactly this looks like. Okay, but let's take this one at a time. First, let's let f of x, let's let it be like our absolute value function. And let's let g of x be, let's do 2 over x plus 3. So first to note is that the domain of f, which will be A here, absolute value is defined everywhere. So that domain is the whole real line. And then the domain of B, the domain of G, which will be B, if you note the bottom part, the denominator can't be 0, so x can't be -3. If you're a little hazy on why this is the domain for G, I recommend going back and reviewing the video on finding domains. All right. So first, let's look at f minus g. So that's going to be, f minus g of x, which by our little list of definitions up there is going to be f of x minus g of x. And so f of x was absolute value, and it's going to be minus g of x was 2 over x plus 3. And that's it. We're done. The domain for this will be A intersect B. And if you do that intersection, I think you will find that it comes out to -∞, -3, union, -3, infinity. And if that was a little fuzzy for you, I recommend you go back and watch the video on intersections and unions towards the beginning of the course, and maybe draw some number lines and check that this is indeed what that intersection is. All right. Let's maybe look at f times g. And so that's going to be f times g of x, which by our rules will be f of x times g of x. And if we write this out explicitly, f of x was absolute value of x, and then g of x was 2 over x plus 3. Maybe we simplify this a little bit and we get 2 absolute value of x over x plus 3. All right, and the domain for this one will be the same thing. A intersect B, which we already saw was this. Negative infinity to negative 3, union negative 3 to infinity. Okay, now let's look at maybe the more complicated algebraic combination. Let's do f divided by g. So that'll be f over g of x. And we saw that that'll be f of x over g of x. And so if we try to calculate this explicitly, f of x is absolute value. So we have absolute value of x over, and then g of x was 2 over x plus 3. And so if we use our compound, or not compound, but if we use our fraction knowledge, our fraction arithmetic, we get that this is equal to absolute value of x times x plus 3 all over 2. And I'm going to simplify that out to be 1/2 times absolute value of x times x plus 3. Okay. Now the domain for this one is going to be A intersect B intersect where g of x is not 0. Okay. But if we note g of x is 2 over x plus 3. Now we know from our discussion about domains and ranges is that 1 over a can never be 0. But that also means that 2 over a can never be 0, right? It's just multiplying it by 2. So g of x is never 0. You could say that maybe a little bit differently. You say g of x is always not 0, right? So the set where g of x is not 0, that's just the whole thing, the whole real line. And so if you do the A intersect B intersect where g of x is not 0, you'll get the same thing that we've been seeing for the others. All right, cool. Let's do one more example. Let's do g divided by f, because it's a little bit different. So this will be g over f of x, which is g of x over f of x. And if we do this explicitly, g of x was 2 over x plus 3 over, and then f of x is absolute value of x. Do some funky fraction footwork here. And I believe what we get is 2 over absolute value of x times x plus 3. Okay. Now, we're going to worry about where f of x is 0. Note f of x, which is the absolute value of x, equals 0 when x equals 0, right? The absolute value of x is only 0 when you plug 0 in. So the set where f of x is not 0 does not have 0 in it. So when we do our domain, or here, that is this set equals It's everything except for 0, which we can write like this. And so then we go to do our domain, which is going to be A intersect B intersect wherever f of x is not 0. That's going to be, remember, A from above was negative infinity to infinity, and then B from above was negative infinity, -3, union -3, infinity. And then intersect, and then we just found that that one was going to be negative infinity to 0, union 0, infinity. And then if you draw some number lines and think about it a little bit, which I recommend you do to convince yourself that this is true, I bet you will find that this pops out to be negative infinity to -3, union -3 to 0, union 0 to infinity. All right, so that last one was a little complicated, but if you keep your wits about you and you remember how we do domains and set intersections, I think you'll be okay. All right, let's switch gears a little bit and let's talk about compositions. Oops, drew a line right through it. That's a bit better. Okay, so let's say we're given two functions. Call them f and g. The composition of f with g denoted FOG, like this. That's not really actually, sorry, that's not really an O. It's like a very tiny circle, like that, whereas an O would be like that big. But some people, like me, are lazy and just call it O. So F composed with G, that is defined as, so we've got F circle G of X is going to be, it's going to be F, and then what you're plugging into F is going to be whatever G spits out when you plug in X. Okay. It might look a little weird if you've never seen it at first, but let's draw a picture and kind of see what's going on. So let's say we have some blob here, call it A, blob here, call it B, a blob here, call it C. Let's say we've got something in A, it's X. And so what G does, so when we look at this function composition, we take X and we do G to it. So we're going to do G and we're going to send it to B. So G is going to hit X and this is going to be G of X. And then what this is saying up here is that once you've done G to X, then you can do F. So now that we've hit G onto X, now what we can do is we take that point that we sent X to by G and we send it with F to another point. So then F hits it and this becomes F of G of X, like that. Okay, so that's kind of the picture of what's going on. But let's see an example of how to calculate these things explicitly. So let's let F of X, let's do something, the X squared plus 2X, and then we'll do G of X will be X plus 2. Okay. So let's look at F composed of the G of X. So we saw that that's going to be F of G of X. And so if we plug in first G of X, I'm going to color coded it first. So I'm going to make this green. So this will be F of X plus 2. So this is what G produced. Okay. Make that white. Don't mix up the colors. There we go. And then we take the green thing and we plug it into F. So this becomes So f of x is x squared plus 2x. So every time we see an x, we're going to replace it with x plus 2. So this will be x plus 2 squared plus 2 times x plus 2. Okay. And so now if we were to calculate this out explicitly, we'll expand this. We'll get x squared plus 4x plus 4 from the squared term. And then from the 2 times x plus 2, we get 2x plus 4. And then if we simplify, we get x squared plus 6x plus 8. All right. Now instead, imagine we wanted to do g composed of f. So we wanted to reverse it, right? Does it get us the same thing out? Who knows? Let's check and see. So this would be g of f of x. And then what we're going to do is we're going to plug in for f of x. So this will be g of f of x is x squared plus 2x. So this will be x squared plus 2x. And then we're going to plug that into g, which is up here, x plus 2. And so then everywhere we see an x, we're going to replace it with x squared plus 2x. So we get x squared plus 2x, and then plus 2 on the outside. And then if we just get rid of the parentheses, we get this. Okay, so yeah, key note here, this in blue is not the same as this in red. So note f composed with g is not necessarily equal to g composed with f. So you got to be careful which order you're doing things in. Okay. Here's the big question though. Why do we care? Why do we care about any of this? You could kind of see maybe why adding and subtracting functions might be cool. It might be useful for modeling things or doing things in real life. But why do we care about composition? Well, you can actually do some pretty interesting things with composition. So let's look at like an application question of this kind of stuff. So let's see an example. We're going to let f of p equal 3p. We're going to let this be the function that describes, describes the total fare f a bus makes in a day. Where p is the number of passengers it has. So if you had 2 passengers in one day, which would be a very small number of passengers, your total fare for that day would be $6, right? Plug in 2 for p. Okay. The Public Transit Authority, they found something interesting. Has found that the function, and it's going to be p of s equal to 0.3 s squared plus 18s. This models the number of passengers a bus line or a bus has in a day. And this is where S is the number of stops the bus makes along its route. Okay, so if you had a bus route that had 10 stops in it, if you wanted to kind of approximate the number of passengers you would expect to see in a day, what you do is you would take 10 and you plug it into this function. So it'd be P of 10. So you plug in 10 everywhere you see an S, because that'd be the number of stops. Okay. So we want to know, what is the function? Describing the total fare a bus would make if it had S stops. So we have a function. Let's get some colors out here. So I have this function here in blue. This describes how many or how much fare a bus will make depending on how many people ride it. And we also have this function here in red that describes how many people will ride a bus depending on how many stops it has. So if we draw like a diagram, so let's do some 3 boxes. So we have stops, passengers, and total fare. And what we saw up above is that F, big F, translates how many passengers we have, the total fare we expect. And our P function that the Public Transit Authority came up with translates how many stops we have in the bus loop to how many passengers we expect to see. Okay. Now, if you remember the diagram from before, if we want to compose these functions, we need to kind of go a little bit backwards. So this will look like FOP. Okay. And if it's a little confusing how I got to this point, I recommend you go up here and look. And in the blue function here, P is passengers. And in the red function here, the function P is passengers. And so the passengers pop up in 2 different places. And so what you're going to do is you're just going to take the green and whoop, put it right in there, which should be the same thing as composing. Okay. So we have FOPS, which is going to be F of P of S, right? Double check that P is indeed in the variable S. That means we've done it right. And so if we do this explicitly, we get F of negative 0.3 S squared plus 18 S. Yes, that is our function. And then we're going to apply F to it, which just multiplies it by 3. So we get this. Excellent. And then if we distribute the 3 inside, we get 0 or negative 0.9 S squared plus, and 3 times 18 is 54 S. And so this right here is the function that describes how much money you'd expect the bus to make depending on how many stops you have for it, which is cool. Because that way you can design your bus routes based on how many stops if you wanted to maximize how much money you're making from the bus routes. All right, cool. So this was an application of composition. Keep working on the homework, keep practicing at it, let it sink in, let it simmer. And I hope to see you in office hours if you have any questions.